Today we are starting discussion on the third module. We start with flow networks. Today we shall see what are flow networks, what are they representing, and why flow networks are included, and also about maximum flow in a flow network. So, the agenda for today is flow network and maximum flow. So, what is a flow network? A directed graph can model the flow of a material in a system from a source to a sink. For example, here is a directed and weighted graph modeling the flow of materials from a factory situated at one cover which produces materials at some rate, and there is a shipping station, suppose at Winnipeg, which ships the materials for supply. Maybe from here there is a sea route or airport, you assume like that, and the material has to reach T to be shipped, and assume that these are road networks. There is a road connecting S and V1 which are junctions, and the numbers are capacity of that road, meaning the truck which is going through that road can hold maximum 16 units of that product, maybe 16 boxes. Assume that there is a bridge or something like that which limits the weight to the weights of 16 materials. Okay, that is the basic information, and given this, the source is here at Vancouver and the sink at Winnipeg. Source produces the material at some steady rate, maybe 20 boxes per day. Assume that in a day only one trip is there, and sink consumes the material at the same rate. That is a property that we need for every flow network that we are going to discuss. If the source is producing the material at the rate of 20 units, then the sink is supposed to consume it at the rate of 20 units itself. Here the assumption is that there is no buffer or storage space for storing extra materials either in the source or sink or in any intermediate stations or junctions. Now you can look at examples, what kind of a flow it is representing or what kind of a material it can represent. The materials can be liquids flowing through pipes. Maybe this is the water tank, and this is a house where water needs to reach, and then it can be liquid or water flowing through pipes. Or it can be parts flowing through assembly lines in a manufacturing company, or it could be electric current flowing through electric networks, or coming to a computer network, it could be information flowing through communication network, maybe 16 units of data. One unit can be some mega bits or something like that. So these are examples. I think with these examples it makes sense. So what are these routes or graphs, etc. And vortices are conduit junction. Conduit is a rod or that connection, pipe or whatever it is for that matter, and vortices are conduit junctions. Now see what is capacity of the routes or edges or conduits. Look at this example. capacity C of UV of a conduit UV, that is for a rod, what is its capacity, is the maximum rate at which material can flow from one end of the conduit to the other end, or from one junction to the other end. What is the maximum rate at which you can send a flow or you can transport some materials? So maximum 14 units, that is the capacity of this route or this conduit. Formally, capacity is a function from a pair of vertices to a real number. For example, the capacity of V2, V4 is defined as 14. So in this figure, the edge labels are capacities. Each edge is a conduit representing a conduit, and on the edge there is a number labeling the capacity. I hope you are getting. And a conduit is a pair of vertices or edge, and that is why it is a function from a pair of vertices to a real number, which is the capacity of that edge or conduit. Now, what is a flow in a network? So, what is shown over here is capacity. No flow is sent, no material is sent. These show the maximum rate at which you can transport materials. Okay. Now, what is a flow? So, here in this figure, a flow is given. A flow f of uv of a conduit uv like this is the actual rate at which materials flow from one conduit junction to other conduit junction. For example, here maybe you can formally define it as a function from the edge or pair of vertices or conduit to a real number, which is the actual flow. For example, the actual flow through this conduit is 11. So 14 is the capacity or the maximum permissible flow, and this is the actual flow. You can see that naturally the actual flow must be less than or equal to 14. That is a property. So I think you are getting. Now we can look at all the properties of a flow network, and in this case you see that flow is 11 and the capacity is 14. Now properties, there are 8 different properties for a flow network. You know that a flow network can be represented as a directed graph, and this is the first property. The capacity of any conduit must be greater than or equal to 0, because there is no point in saying that you can transport minus 2 boxes. That is meaningless. 0 means okay, you cannot transport anything through that route. That is allowed, but negative numbers are not allowed as capacity. And what is next? For every conduit UV, VU is not a conduit, or if there is an edge from U to V, you cannot have the reverse edge. In a graph you can have, but why is it that you may think if it is a road network, if there is a road which is not a one way, definitely there must be the opposite. But see here, it is a flow network, and the basic objective is to model the flow of materials from a source to a sink. So in that case, suppose you say that from the vertex U, that is the conduit junction, to the vertex V, there is a flow. You will never come back, because your aim is to reach into the other vertex. So once you flow from one vertex to the other, no need to come back. That is not good, and that is why the reverse edges are not allowed. That is the second property. Third property, self loops are not allowed. There is no point in starting from U coming back to U, because your purpose is to go from the source to the sink by taking minimum time. Okay, so minimum number of edges. So self loops are not good, not allowed. And there must be a source, one of the vertex. Similarly, one of the vertex must be a sink. In the given example, Vancouver was the source and Winnipeg was the sink. Now for all conduit junctions or vertices other than the source and sink, the any other vertex must lie in a path from source to sink. That means you cannot get into a situation where you reached into a junction from which there is no outgoing edges or it is not possible to proceed. Such a situation is not allowed, or in other words, what is G is a connected graph. You can verify that these are equivalent. It is a connected graph. You will never end up in a dead vertex. Dead vertex means you cannot move out. Then the next property, which is the capacity constraint that we already identified, on any conduit or edge, the actual flow must be less than or equal to the capacity of that edge or conduit. That is a very reasonable and intuitive requirement. And finally, this equation, for every vertex u, the total flow, total actual flow or total inflow entering that vertex must be same as the total flow leaving that vertex. I will explain it with an example. In this example, if you take u as this vertex, you can see that the total inflow, that is the total actual flow coming to that vertex, is 12. It is 8 through this conduit and 4 through this conduit, no other incoming edges, only 2, and through that a total flow of 12 is coming to that particular vertex. So the total inflow that is represented by this quantity is same as the total outflow is what it is saying. Now you see what is the outflow from that vertex. It is 1 through this conduit and 11 through this conduit. So it is 12. So this is what this property is saying. For every intermediate vertex, the total flow coming to that vertex must be same as the total flow leaving that vertex. That means conduit junctions have no capacity to store materials. Whatever is the total amount of materials coming to that particular vertex or conduit junction, it must flow out. That also is an essential property. So these are the 8 properties that we need to have for a directed graph to be a flow network. Now we can see what is the value represented as modulus f for a given flow. Example, a flow is given, okay. Now the value of this flow represented as this is defined as the total outflow from the source vertex minus the total inflow to the source vertex. That must be 0 for all vertices other than source and sink, and the flow or the net flow is nothing but the total outflow from the source vertex minus the total inflow, if any, to the source vertex. In this example, the total outflow is 11 plus 8, which is 19, and the total inflow is nothing, 0. So it is 19, or effectively it is the net flow out of the source vertex. That is the flow going out of the vertex minus the total flow coming into the source vertex. In this case, 11 plus 8, 19 is the total outgoing flow and 0 is the total incoming flow, and the net is 19, and which is what is called the value of a flow in a given flow network. It is the net amount of materials flowing out of the source vertex. So definitely it is a total outflow minus total inflow, because suppose it sends out 19 units and at the same time it is receiving through some other edge, say 2 units, then the net must be 70. I hope you are getting it. Now Till now we have seen a network where only a single source vertex is there and a single sink vertex is there, and you can have a situation where you have a number of production units at different places for a company, and also different sinks may be there, different destinations or different shipping stations may be there. To fit into our definition of flow network, we cannot allow this. We should have a unique source and a unique sink that we can obtain from this kind of a network like this. What you do is, you add a new vertex and call it as a source vertex and add conduits of infinite capacity to all the existing source vertices. There is no restriction. You can send the sum of the capacities of all the outgoing edges from here. You can set it as the sum of those or infinity. Similarly, you can add a new vertex as the sink and add infinite capacity conduits reaching to that from the existing sink vertices. This is a very simple technique to make it a flow network. So you can assume without loss of generality that a flow network is going to have a unique sink and a unique source. Then the maximum flow problem. This is a very common problem that computer science students should learn in algorithms course or graph theory, which is a max flow problem. Given a flow network G, which is a graph with vertices and edges, and we know that there is a unique source and a unique sink, then the problem is to find a flow such that the value is maximum possible for that flow network. For example, here you are given with a flow network and a flow. Flow is also shown. And what is the value of the flow? The total outgoing from S minus total incoming, which is 19 because no incoming, 11 plus 18. And on the same flow network you can have another flow. Not that it is the same network in the sense that the capacities are all same and conduits are all same, but flow is different. You see here that you have a net flow of 11 plus 12, which is 23. So between these two, the max flow is this one, F2, with a flow value 23. And now I hope you are getting the problem. Given a flow network, the flows are not given, only the capacities are given. You have to come up with the maximum flow possible. If all the flows are also given, you can just find the maximum, but flows are not given. You need to find a max flow in a given network where only the capacities are shown. Okay, that is the problem. And in this particular case, one can prove that this is a max flow. It is not possible to have a flow with value more than 23. Okay, with this we are finishing this lecture. Today we have seen flow networks and max flow problem. A flow network is a directed graph and directed and weighted graph satisfying a set of 8 properties. And in a flow network, each edge or conduit represent a medium of communication between two conduit junctions, and each such conduit is characterized by a number which is the capacity or the maximum flow that is permissible through that particular conduit. And what is a flow? Flow is the actual rate at which materials flow through a network. And the net value of a flow in a network is the net outflow from the source vertex. And later we can prove that it is same as the net inflow to the sink vertex. And for all vertices other than the source and sink, the net flow is 0. That is, the total incoming flow or inflow is same as the total outgoing flow or outflow. This is a property that we have seen, and with this we are finishing this lecture. Thank you.